Distance is the most honest thing in physics. You want to know how far it is from here to the door? You get a tape measure, you stretch it out, you read the number. 14 feet. Done. Nobody argues. Nobody interprets. Nobody writes a philosophy paper about it. 14 feet is 14 feet. You want to know how far it is to the moon? You bounce a laser off a mirror the astronauts left up there and time how long the light takes to come back. About 239,000 miles, clean, solid, unambiguous. The one measurement in all of science that never lies. That's completely wrong. And I can prove it. See, I used to feel the same way. Distance felt like bedrock. You stand here, the wall is over there, and the gap between you and the wall is a fact about the universe. Not an opinion, not a perspective, a fact, something that exists independent of you. Whether you look at it or don't look at it, whether you walk toward the wall or run away from it, the gap has a definite size. And for a very long time, the smartest people who ever lived agreed with that feeling. Euclid built his entire geometry on it. He had 5 postulates, and the whole system rested on the idea that space is a fixed, rigid, eternal container. Lines have definite lengths. Triangles have angles that add up to 180 degrees. Parallel lines never meet. And the distance between 2 points is the distance between 2 points, period. Newton felt the same way. He needed a stage for his physics, and Euclidean space was that stage. Absolute space, he called it. A vast, invisible, unchanging grid. Objects move through it. Forces push them around. But the grid itself is permanent. The distances on that grid are written in stone. And honestly, this worked spectacularly well for over 200 years. Engineers build bridges using Euclidean geometry, and the bridges don't fall down. Ships navigate oceans with it. Surveyors carve up land with it. The whole Industrial Revolution was built on the assumption that a foot is a foot is a foot, everywhere and always. So what's the problem? The problem is that nature doesn't care about your tape measure. Let me set the scene. It's 1905. A young clerk in a patent office in Bern, Switzerland, has been thinking about light. Specifically, he's been thinking about something peculiar that James Clerk Maxwell's equations seem to imply. Light travels at a fixed speed, about 186,000 miles per second, and that speed doesn't depend on how fast the source is moving or how fast you're moving when you observe it. That's bizarre. If I'm on a train and I throw a baseball forward, you standing on the platform see the baseball moving at the train speed plus the throwing speed. That's just how velocities add. But light doesn't play by that rule. Light always arrives at the same speed, no matter what. This young man, Albert Einstein, takes that fact seriously. Dead seriously. He asks what has to change about our understanding of space and time for the speed of light to be truly constant for all observers. And the answer shakes everything. Here's what he found. Imagine 2 people. One is standing on a train platform. The other is riding past on a train moving at, let's say, 80% of the speed of light. Unrealistic, sure, but that's how thought experiments work. You push things to the extreme so the effects become visible. Both of them have rulers. Both of them are measuring the length of the same object, say a boxcar on the train. The person riding on the train lays her ruler alongside the boxcar. She's careful. She's precise. She says 40 feet. The person on the platform watches the boxcar fly past, makes his own measurement, accounts for the time it takes light to travel, corrects for every conceivable source of error, and he gets a different number. He says 24 feet. They argue. They check each other's math. They call in other physicists. And the verdict comes back. Both measurements are correct. The boxcar is genuinely 40 feet long in the frame of reference, riding with it. And it is genuinely 24 feet long as measured from the platform. These aren't mistakes. These aren't optical illusions or artifacts of sloppy technique. When you strip away every possible source of confusion, the disagreement remains. The distance is truly, physically, irreducibly different depending on how fast you're moving relative to what you're measuring. This is called length contraction, and the formula is simple but devastating. The faster you move relative to something, the shorter it gets in the direction of motion. At everyday speeds, a few miles per hour, the effect is unmeasurably tiny. But as you approach the speed of light, the contraction becomes dramatic. At 99.9% of light speed, a 100-foot object shrinks to about 4.5 feet. The object itself doesn't feel squeezed. In its own frame, it's the same as it ever was. But from your frame, looking at it fly past, It's been compressed to almost nothing. Sit with that for a second, because what just happened? Distance, the most trustworthy quantity in physics, the one thing we all agreed on, just became a matter of perspective. It depends on your state of motion. It is not a fact about the world. It is a fact about the relationship between you and the world. And that is a completely different kind of thing. You might try to save the situation. You might say, well, one of those frames is the real one. The rest frame, the one where the boxcar is sitting still, that's the true length. But relativity says no. There is no preferred frame. No frame is more real than any other. The laws of physics work the same in all of them. The person on the train has just as much right to say she's sitting still, and the platform is the one zooming by. And from her perspective, it's the platform that's contracted. Both of them are right, which means neither of them has the real distance. There is no real distance. There's only the distance according to each observer. So whose distance is real? Neither. Or both. That's the revolution. But hold on. Maybe you're thinking, all right, things get strange at near light speed. That's exotic. It doesn't affect my morning commute. And you'd almost be right. Almost, because the trouble doesn't stop with special relativity. It gets much worse. 10 years later, Einstein publishes general relativity. And this theory doesn't just say that distance depends on your speed. It says that distance depends on what else is around. Imagine you're floating in deep space, far from any planet or star. You stretch a rigid rod between two small markers you've placed in the void, and you measure the gap, 10 meters, solid, reliable. Now I take a massive star, something with 10 times the mass of our sun, and I park it right next to your two markers. The rod still looks the same, but if you try to verify the distance by timing a light pulse bouncing back and forth between the markers, you find the light takes slightly longer than before. The space between those markers has expanded, not because anything moved. The markers are right where you left them. The space itself, the actual geometry of the region between them, has been altered by the presence of mass. This isn't metaphorical, this is literal geometry. Near a massive object, the rules of Euclid break down. The angles of a triangle drawn in curved space don't add up to 180 degrees anymore. Parallel lines bend toward each other. Circles have unexpected circumferences. And distances measured through regions of curved space are longer than they appear on a flat map. It's as if the space near a heavy object is deeper than it looks, like a valley that's wider at the bottom than the rim suggests. Walking through that valley takes more steps than you'd predict from studying the view up top. Near a black hole, this becomes monstrous. Two markers that appear from a great distance to be a few miles apart might have an enormous proper distance between them. You'd fly and the destination wouldn't get closer, because every meter of space near the event horizon is stretched and dilated by the extreme curvature. Distances become elastic. Geometry becomes unreliable. The map is not the territory, and in general relativity, the map can be spectacularly, almost maliciously wrong. Now, if I were a student in the audience right now, I'd raise my hand and say, Professor Feynman, this is all very dramatic, but I've got a ruler right here. It says 12 inches. It said 12 inches yesterday. It'll say 12 inches tomorrow. What's the problem? And I'd smile at that student because he's making the same argument Newton would have made. He's saying, look, in my everyday life, distance works perfectly. And he's right. It does. But so does the idea that the earth is flat if you never leave your neighborhood. The question is not whether the approximation works. The question is whether it's the truth. And those are very different questions. Let me make it worse. Let's zoom all the way out. Not one star. Not one black hole. The whole cosmos. In 1929, Edwin Hubble measured the light from distant galaxies and found something that changed everything. The farther away a galaxy is, the faster it's moving away from us. This looks like an explosion, like we're at the center of some cosmic blast and everything is flying outward. But that's the wrong picture entirely. The galaxies aren't flying through space. The space between them is growing, new distances being created, manufactured right there in the gaps moment by moment. The galaxies are, in a sense, sitting still on the fabric. The fabric itself is stretching. This isn't something the galaxies are doing. This is something space is doing. And it's been doing it for about 13.8 billion years. So when I tell you the Andromeda Galaxy is about 2.5 million light years away, I'm already in trouble. Which 2.5 million light years do I mean? The distance right now. The distance when the light I'm seeing left Andromeda. The distance it'll be by the time I finish this sentence. These are different numbers, and for very distant objects they're wildly different numbers. A galaxy whose light has been traveling for 12 billion years is not 12 billion light years away today. It's more like 30 billion light years away right now because the space between us has been expanding the entire time the light was in transit. And that 30 billion light year figure doesn't correspond to anything you could have measured at any single moment. It's a calculated quantity, a model-dependent output. You feed in assumptions about how the expansion rate has changed over cosmic history, and out pops a number. Change your assumptions, change the number, and it gets messier. And astronomers use at least 4 or 5 different definitions of distance for faraway objects. There's the light travel distance, which is just how long the photon was in flight. There's the proper distance right now, which accounts for all the expansion that happened along the way. There's the angular diameter distance, which tells you how big an object appears on the sky. There's the luminosity distance, which tells you how bright something looks compared to how bright it actually is. For nearby things, a star in our own galaxy, these all give practically the same answer. But for a galaxy near the edge of the observable universe, these numbers can differ by factors of 2 or 3 or more. Which one is the real distance? None of them. Or all of them. Each answers a different question, and none of them is the single, simple Euclidean number you wanted. Distance, at cosmological scales, is not something you simply measure with a tape. It's something you compute. And the answer depends on which question you're really asking. By now, the old Euclidean notion is in ruins. A ruler between 2 points does not give you a fact about the universe. It gives you a number that depends on your speed, the gravitational field you're sitting in, the expansion history of the cosmos, and your choice of definition. So I owe you something better than ruins. Let me rebuild. In special relativity, there is a quantity that everyone agrees on. It's not distance, it's not time, it's a combination of the two. It's called the space-time interval. 2 events happen, say 2 firecrackers go off, one here and one over there, a few seconds apart. You and I might disagree about how far apart they are in space. We might disagree about how much time elapsed between them. But if we both compute a particular combination, time squared minus distance squared, adjusted with the right factors, we get the same number. Every observer, regardless of their velocity, agrees on the interval. That's the real thing. Not distance alone. Not time alone. The interval. Here's an analogy that helped me. Think about a tall flagpole on a sunny day. Depending on the angle of sunlight, the shadow it casts on the ground changes. In the morning, the shadow stretches long to the west. At noon, it's short, right under the pole. In the afternoon, it reaches east. The shadow keeps changing. But the pole doesn't. The pole has an actual fixed 3-dimensional height. What changes is the projection of that height onto the 2-dimensional ground, and that projection depends on the angle of the light. Distance is that shadow. When you measure a distance, you're projecting the interval onto the spatial slice of your particular reference frame. Different frame, different projection, but the interval itself doesn't budge. This means space and time are not separate containers. They're woven together into a single 4-dimensional fabric. Space-time. And the true geometry is the geometry of space-time, not the geometry of space alone. Minkowski saw this clearly back in 1908. He said space by itself and time by itself are doomed to fade into mere shadows, and only the union of the two preserves independent reality. He was absolutely right. In general relativity, space-time gets richer still. The interval isn't flat and uniform. It varies from place to place. The mathematics uses something called the metric tensor, a field defined at every point in space-time that tells you how to compute the interval between neighboring events. The metric encodes all the curvature, all the stretching, all the warping, change the distribution of mass and energy, and the metric reshapes itself. Geometry becomes dynamic, it breathes, it responds. Think of the ocean surface again. If you want the distance between 2 boats, you might stretch a rope across the water, but the surface is heaving. Swells lift the rope, troughs drop it. The measured distance along the surface depends on the state of the sea. Calm water gives one answer, a storm gives another. Space-time is like that. Not a still pond, a living surface where geometry rides the waves of matter and energy. Now, one more step, and this one is the most unsettling of all. Quantum mechanics, the other pillar of 20th century physics. And in the quantum world, distance gets strange in a way that has nothing to do with speed or gravity. You prepare 2 particles in a special correlated state. Entangled, we call it. Their properties are linked at the quantum level. Then you separate them. One goes to one side of the lab, the other goes to the other side. Or one goes to Earth and the other goes to a satellite orbiting the planet. Or one stays here and the other sails off to the far side of the galaxy. Doesn't matter. Measure one of them, check its spin, say, and instantly the outcome tells you the spin of the other particle, not approximately, not statistically. Exactly. Your first instinct might be to shrug. They were programmed in advance. Like a pair of shoes in two boxes. Open one, find the left shoe, and you know the other box has the right shoe. What's the mystery? But a physicist named John Bell worked out in 1964 a precise mathematical test to distinguish the programmed shoes explanation from something genuinely stranger, and the experiments, performed many times in many labs with exquisite care, come down on the side of strange. The correlations between entangled particles are stronger than any pre-existing programming could produce. The measurement on one particle is affecting what you find when you measure the other, and the distance between them makes no difference. 1 meter, 1 million miles, 1 billion light years. The strength of the correlation doesn't weaken, it doesn't fade. It doesn't diminish with distance the way gravity weakens or a signal fades. Entangled particles don't experience separation the way billiard balls or planets do. In some very real quantum mechanical sense, they are not far apart at all. The quantum state they share doesn't inhabit ordinary three-dimensional space. It lives in a larger, more abstract mathematical arena, where the concept of spatial distance doesn't apply. You can't send a message this way. No information travels faster than light through entanglement. Causality is safe, but what the phenomenon reveals is startling. The quantum world organizes itself according to connections that have absolutely nothing to do with how far apart things are. Two entangled particles on opposite sides of the galaxy are more intimately linked than two unentangled particles touching each other on your desk. Distance, in the deepest quantum sense, is irrelevant to what matters most. And here's where a handful of very clever people have pushed the idea to its logical extreme. Mark van Ramsdonk and others working at the boundary of quantum gravity and quantum information have proposed something radical. Maybe space is not fundamental. Maybe distance is not a basic ingredient of reality. Maybe it's emergent, the way temperature emerges from the motion of molecules. No single molecule has a temperature. Temperature is a collective property, a statistical summary of what trillions of particles are doing. What if distance is the same kind of thing? What if two regions of the universe are near each other because the quantum degrees of freedom in those regions are heavily entangled, and far from each other because their entanglement is thin? In this picture, space is not the arena in which physics happens. Space is the scoreboard. It's a readout of how entangled things are with each other. Cut the entanglement between two regions, and you don't just disconnect them informationally. You tear the space between them. You create a geometric gap, a rift. Distance, in this view, is not something that exists first and then things happen inside it. It's something that emerges from the pattern of quantum correlations underneath. There's a beautiful thought experiment that illustrates this. Take two black holes entangled with each other. According to the calculations of Juan Maldacena and Leonard Susskind, the entanglement between those black holes corresponds to a wormhole, a tiny bridge of space-time connecting them. Entanglement equals geometry. More entanglement, more connection. Shorter effective distance through the bridge. Less entanglement, the bridge narrows and eventually snaps. The geometric connection between two regions of space-time is literally the same thing as the quantum entanglement between them. If that idea holds up, then space is stitched together by entanglement. Pull the threads, and the fabric tears. I want to be honest. This is not settled science. It's a research program. The calculations work beautifully in simplified models, lower-dimensional toy universes that are cousins of ours, but not quite the real thing. There are suggestive results from the study of black holes, where entanglement and geometry seem most tightly wound together. But a complete theory, one that derives the three-dimensional space of our everyday experience from quantum entanglement in full generality, does not yet exist. Still, the direction of the evidence is remarkable. Every time we dig deeper into what distance really is, it gets less solid, less primitive, more like an approximation of something underneath. And the hints from quantum gravity keep pointing the same way. So where does all this leave you? You came in with a ruler and a conviction that the gap between two things is a plain fact about the world. And I've pulled that conviction apart, layer by layer. Speed warps it. Gravity reshapes it. Cosmic expansion makes it a moving target. Entanglement ignores it entirely. And at the deepest level we can currently probe, distance looks less like bedrock and more like condensation on a cold glass. Something that forms on the surface of a process we haven't fully understood. And yet, tomorrow morning you'll get out of bed, walk to the kitchen, and the coffee pot will be exactly as far away as it looks. The floor will be solid under your feet. The Euclidean description works magnificently at human scales. Carpenters cut boards to the right length. Pilots land on the correct runway. Nobody needs to worry about space-time intervals while driving to work. That's because the approximation is superb. Within its domain, it's practically perfect. But it is an approximation. And the real thing underneath it, the actual geometry of reality, is richer and stranger and more beautiful than anything Euclid or Newton could have dreamed. What keeps me awake, what I find genuinely thrilling, is the question that sits behind all of this. If distance isn't fundamental, then what is? What are the true ingredients? What is the universe actually made of, at the deepest level, before space and time crystallize out of it like frost forming on a cold window? We don't know. Nobody knows. But the fact that we can formulate the question, that we've managed to peel back this layer and glimpse that something lies beneath, tells me we're pulling on the right thread. And whatever the answer turns out to be, I suspect it will be stranger than anything we've imagined so far. So the next time you look up at the night sky and someone says that star is 400 light years away, ask yourself 400 light years according to whom? Measured how? At what moment? In whose frame? And if the answer is tangled and complicated, don't be frustrated. Be amazed. Because that complexity isn't a failure. It's nature showing you how much deeper it goes than any ruler can reach. But the space between you and that star is not a line drawn on a blueprint. It's a living, shifting, observer-dependent, possibly emergent thing. And the fact that the starlight still reaches you, crossing all that ambiguous distance to land quietly on your retina, should feel a little more miraculous tonight than it did 25 minutes ago. If you had to guess, what do you think space is really made of? I'd love to hear what you come up with.